All right. Uh, let's get started from where we left off. So we want to define threshold voltage, and this is a very important thing because this is what we will use in the problems, and in the MOSFETs also threshold voltage plays a very important role. So what is threshold voltage? Okay. So we have defined what is threshold. We said that threshold is that voltage at which the surface inversion charge is equal to the bulk doping, right? So let me show you. Okay, by mistake I have put phi s. Let's call this phi s, okay, because I've shown psi s, but I want to refer to this as phi s. That will make the notation consistent. That's why I changed. In the last lecture I have used psi s, but now we want to use phi s. Okay, so we'll consider NMOS and PMOS devices. Okay, in NMOS device, we said if the doping density was, let's say, Na, the NMOS device means it's a p-type substrate, correct? It's a p-type substrate, and if the doping density was Na, the phi f is given by this. This is now by routine expression for us, phi f. For a PMOS device, we can give that as minus kT by Q Ln. This is N-type doping in the substrate. N-type substrate. Here it is p-type substrate. Okay. So we can calculate phi f directly. Now what is accumulation? What is threshold? What is inversion? So just an axis of surface potential. Whenever your surface potential was less than 0, it was accumulation, right, for an NMOS device, because that will accumulate holes in the interface. And between 0 to 2 phi f, it was called depletion. We are pushing away the holes. But once we cross 2 phi f, it's inversion because we are creating electrons at the interface. So this was NMOS device, which we have seen in detail. The exact opposite thing happens in a PMOS device. Whenever your surface potential is greater than 0, it is accumulation. Why? Because it's an N-type substrate. You apply a positive voltage, positive surface potential, you will accumulate holes. So that's why it is accumulation. And once you go, surface potential goes from 0 to 2 phi f, it is depletion. And if you increase beyond 2 phi f, we call it inversion. So for example, if I take my ND to be 10 power 15, okay, 10 power 15 phi f is going to be 5 times 60, so 0.3 volts. Okay. So if your surface potential is greater than minus 0.6, that means minus 0.7, minus 0.8, and so on, it will be inversion. Okay. So this is a simple way of remembering this. Okay. And we have also defined what is threshold voltage. So threshold voltage, this was originally called as phi s, but phi s equal to 2 phi f. That's why we can write it like this. So this is an expression to calculate threshold voltage. And what is QD? What is the amount of depletion charge at threshold? We know that at threshold, your surface potential is 2 phi f. So the amount of depletion charge is going to be, okay, we have to calculate. We'll do that. Na times Na or Nd, it could be anything, times, okay, Q times Na times W, width, right? That is what we need to calculate. Okay, we'll calculate that. Okay. One important point I want you to note is in our definition of VT here, this is the definition of VT, right? In ideal NMOS device, we are uncovering acceptors. So the QD will be negative. Okay. If QD is negative, so this is going to be negative. So VT is going to be, so negative of negative, this is going to be positive number plus positive number, right? Because 2 phi f is positive. Remember, 2 phi f is positive at inversion, right? For inversion threshold. So the total VT is going to be positive for a NMOS device. So that's why we wrote QD is negative. Psi s is positive, not some. Okay. Sorry, this is, read it as phi f, phi s. Phi s, okay. Phi s is positive and VT is positive. Whereas if you had an ideal PMOS device, QD is positive, right? So the first term is negative overall, minus QD, so it will be negative. And surface potential is negative. So the second term also is negative. So VT is negative for a PMOS device. For an NMOS device, VT is positive. For a PMOS device, VT is negative. So I want you to note this complementarity. It is very important for us later on. Okay? In CMOS, this is very essential. This complementarity in the voltages. All right. So fine, let's try to solve some problems. Okay, so much of theory, right? So let's look at this band diagram and let's calculate what is its surface potential. How do we do that? Well, we know that surface potential can be calculated by uh, what was the definition? Surface potential phi s is equal to EI in the bulk minus EI in the surface. Right? That's the definition of surface potential. So we need to use something as a reference. So I'll say use PF as reference. So this is going to be how much? Well, it's shown here in the graph. So the distance of EF from EI is 0.3. Okay, it's plus 0.3 volts. Okay, at reference to EF, EI is at plus 0.3. Minus EI at surface is at EI, right? So this is going to be 0. So this is going to be 0.3 volts. This is just surface potential. Phi s is equal to 0.3 volts. Okay. Do it for inversion also, do it for accumulation also, and see for yourself. Okay. What is the applied gate voltage when you look at this particular band diagram? Well, the gate voltage is simply the displacement of EF in the semiconductor, and with respect to the semiconductor, what is the displacement of EF in the metal, right? So metal work function has been pulled down here, and this is EF in the semiconductor. The distance is 0.6. So the applied gate voltage VG must be 0.6 volts. Just from the band diagram we are assuming. What is the depletion width? Well, this could be tricky, right? So how do you calculate the depletion width? Well, we know the depletion width formula, right? We have done it now, starting with PN junctions multiple times. So 2 epsilon silicon by QNA times phi s. So whatever is the surface potential, you calculate based on that, you can calculate. So we know surface potential. So what is this? Is going to be this. No, there's nothing in this calculation except that, I want you to note this 11 point, I don't know, it's 11.7, 11.8, take it as 11.7 into 8.85 into 10 power minus 14 farad per centimeter. Please note this 10 power minus 14 we are using because in semiconductors we tend to use all the length units as centimeters. Okay, it is convention, nothing more than that. So this is divided by, if you forget that, you will definitely not get correct answers. Okay, NA, how much is NA? Well, we didn't calculate NA, but is it available to us, NA? Well, NA is simply the distance of Fermi energy from EI, right? In the bulk. So in the bulk, this is given. This is phi f, right? So phi f equal to KT by Q ln of NA by NI. And we said it's 0.3 now. This is equal to 0.3. So NA, as my approximations, my style of approximation, 600 millivolt into phi, right? So this should be 10 power approximately per centimeter cube. This should be the approximate answer. So put that here. So per centimeter cube, remember, okay, 10 power 15 centimeter cube times phi s is 0.3. You have to solve for this, and I don't know. I mean, you just can always calculate this. This should be some microns. It will be okay, less than a micron, or so it will be, okay, or close to that. You have to see. Okay, you calculate that and verify. You substitute. You calculate. Okay. All right. So this is one of the ways, one of the simple problems that you can have. Another problem: a MOS capacitor is maintained at T equal to 300 degrees Kelvin, and TOX is given to you as 0.1 micrometer, and accepted doping is 10 power 15 per centimeter cube. Compute the gate oxide capacitance. Okay, what is the gate oxide capacitance? Gate oxide is simple parallel plate capacitor. You have a metal and it's replaced by an oxide, right? That's all we want. Only the oxide capacitance we want. Okay, so I mentioned this in one of the previous lectures. Cox equal to epsilon oxide divided by thickness of the oxide. Epsilon oxide will be 3.9 into 11.7 into 10 power, 11.7 into 8.85 into 10 power minus 14 divided by TOX is 0.1 micron, but we have to mention it in centimeters. So 0.1 micron is 10 into minus 4 centimeters. So overall it will be 10 power minus 5. So this is 1 into 10 power minus 5. I can cut it out. So basically I'll have 4 into, oh well, I made a mistake. You see here, I made a mistake. So I took epsilon oxide, I put 3.9, which is the relative permittivity, right? See here, this is epsilon relative for SiO2, and for no reason I brought in 11.7. That is epsilon relative for silicon. I don't need this. Okay, so this number should not have been there. That's my mistake. Okay, this you should strike it off. Okay. So what is it going to be? 4 into 8, 32, right? But it's 8.85. 4 into 9 is 36. It will be between 32 to 36. Sorry, 32 to 36 into 10 power minus 5. I'll take it. So 10 power minus 9 farad per centimeter square. 32 to 36, some number in between that. You calculate it exactly. Okay. So essentially, if I take the upper bound, it will be approximately 36 nanofarads per centimeter square. Upper bound. Okay. All right. So what is phi f? Now, instead of giving the band diagram, I'm asking, give the numbers and calculating the Fermi energy. This is going to be simply kT by Q ln and A divided by Ni. So this will be, okay, I shall write it a little bit more clearly here down. So this will be 60 millivolts into 10 power 5 or 10 power 15. So 10 power 5, yeah, 10 power 5. Oh, sorry, not 10 power 5, 5. Making a lot of mistakes. 0.3 volts. Okay, this is phi f. What is width when psi equal to phi f? Well, the same thing that we did last problem. Width is always square root of 2 epsilon by Q and A times phi f. At psi equal phi s equal to phi f. So this will be the width. We will calculate what it is. What is the electric field at the interface? This is important. This is interesting, right? How will you calculate the electric field? So remember electrostatics always. So if you don't remember the expression, no worries. dE by dx equal to rho. In this case, this should be equal to Q and A by epsilon silicon. So this should be epsilon silicon here, right? Integrate it. You should get a line, straight line. At, we know that in the bulk it goes to 0. At the surface it will be peak. So essentially this will turn out to be electric field equal to Q and A divided by epsilon silicon into width of the depletion region. So you already calculated the width here in the third part. Substitute that width and calculate the electric field, and it will turn out to be something in the order of 10 power 4 volts per centimeter, something in that range. Okay. So please make sure that you do that. Okay. So this is how you solve a few problems. So I know I have spent a lot of time explaining the concepts this week, but those are essential to understand MOSFETs in depth. Otherwise, we'll be talking about, if you ask built-in voltage, you will say that it is simply ln Na Nd by Ni square or things like that. The formulas are meaningless unless you have a physical understanding. Okay, Np equal to Ni square is meaningless. We need to understand what it means. Np equal to Ni square. What does it mean? Np is not equal to Ni square, right? We need to understand all these physical things. Only then we will understand it in depth. You might be wondering, why do you want to have so much of deep understanding? Well, the reason is right now we are in 7 nanometer technology, and we are actually going even smaller than that. So the technology is evolving very fast, and our syllabus also has to evolve like that. We should not be happy solving, formula-based questions. We need to develop a deeper insight so that we understand the state of the art. Okay, so that's why we are introducing a lot of concepts into this curriculum. Okay, all right. So I wish you good luck. Please take your time. review all these videos. I'll also quickly record another video wherein I'll show you NanoHub, how to use NanoHub to analyze some of these mass capacitors. Okay, so it'll be interesting. I'm sure. Just take your time, try it out. We'll give you a couple of assignment problems based on running the NanoHub tool. So once you do that, you'll be all set. In the next week, we will discuss more about capacitors and what happens. Some of the effects we will discuss. Okay, so I'll meet you there. Thank you so much.